Let's get started. So welcome to our presentation today about Iceberg Geo data tab. And you guys hear me okay from the back? Awesome. Cool. My name is Jia. I'm a co-founder of Variables and also the PMC chair of Apache Sedona. Today I'm here together with my friend Zihang.
Hi.
Sure.
Yeah, I'm Sihan. I'm working Databricks. I'm in Spark team, but previously I worked on Iceberg at Apple, Iceberg PMC member.
Cool. Great. I think many of you in this room probably have heard of geospatial data or probably have been using geospatial data, right? So geospatial data nowadays is become increasingly important, right? From logistics to urban planning to climate, right? You have geospatial data everywhere. However, managing geospatial data at scale presents some very unique challenges, right? So today we're going to walk you through that. How can we solve that problem, manage geospatial data at scale using Iceberg, right? And how we started and how the Iceberg Geo data tab works in general. Cool. Let's move on. Some forward-looking statement. Okay. Agenda today, right? So how we started, so why we start to talk about Iceberg Geo data tab in Iceberg, and also then Zhehong going to talk about the journey and the design of this tab. And finally, if we still have enough time, I'm going to give a quick demo about how that looks like and how you can use Iceberg, right? Cool. Let's move on. All right. So yeah, so we all know Iceberg is great, Parquet is great, right? However, so what do we use before that? So what do we use in the Geo community before that? So there are many existing Geo data file formats in the past, right? So you guys probably already know some of them, like TXT file with WKT, WKB, shapefile, GeoJSON, so on and so forth, right? So there's one thing I often talk about to my friends is that so our geospatial folks are really good at reinventing the wheel, right? So in the past decade, we invented probably like 80 different file formats for every single different scenario, right? So you probably need a really specific tool to actually handle all these formats. So all these formats create data silos, right? It is really hard for you to actually make sense of geospatial data together with your existing data infrastructure. So actually, so realize that problem. So a couple of years back, so there is this GeoParquet project started. So GeoParquet is a community effort started in 2022. So what it does is, so it defines a cloud-native data format that built on top of Apache Parquet format, and it defines how you describe a geospatial data tab, and how do data encoding for geometry data tab, and how you do spatial statistic bounding box inside Parquet, right? So GeoParquet is really successful, and there are many projects started to adopt GeoParquet, including GeoPandas, Google BigQuery, Apache Sedona, right? And also there are many spatial data vendors start to release geospatial data using GeoParquet format, so such as Foursquare, such as Overture Map Foundation, right? Great, so now we have geospatial support in Parquet file, but what about Iceberg? What about all those cool features in Iceberg, such as asset transaction, data governance, so on and so forth, right? So what can we do about that? So actually, people have been thinking about that for a very long time. People really want to support geospatial data in Iceberg. So actually, go all the way back to 2021. So actually, the first Geo issue already created on Iceberg GitHub repository. And actually, in 2023, so there is a couple research projects, including GeoLake, started to think about how can you add geospatial data tab into Iceberg. So in late 2023, so Variables, so my company, so we created a fork of Iceberg called Havasu and added geospatial support into Iceberg, and we made it to production and opened it up to our customers. And given all the activities going on in the community, so officially in around early 2024, the community started to think about, so how can we actually move away from all these forks and really put geospatial data tab as a native data tab into Iceberg and enjoy all the benefits of Iceberg, right? So in early 2024, so we started conversations, and many companies were involved in the overall process. And so I'm going to talk about all details here. It is like year-long discussion. There are many topics to be covered. And finally, earlier this year, February 2025, so Iceberg Geo data type definition is officially merged into Iceberg v3 spec. You probably have heard of this many, many times from Run, from Databricks folks as well, right? So this is going to become a big thing in Iceberg v3 spec, and we're going to have implementation for that as well. Cool. Now I'm going to hand it over to my friend.
Yeah. Thank you, Ja. So I'll talk about it from the other point of view. So before I met Ja, like this, we were just in the Iceberg community, and how we came to want to support Geo. So the situation, I think what happened was just like the Geos folks and then the big data folks were got very specialized, right? Different communities, and there was just kind of a lack of knowledge of the other side. So that's why it took really long time for things like Iceberg to support Geo. I think what happened was the GeoParquet, he mentioned GeoParquet was already kind of adopted, and later on I know, Chris and Ja worked really hard to get that adopted. But GeoParquet was actually an extension of Parquet. It didn't actually work with the Parquet community that closely. So still the two communities still don't really know each other that well. And it took, I think, Iceberg not having a extension mechanism to force us to talk to each other, because otherwise you could have extended Iceberg. I think from our side, yeah, we just felt like we didn't know enough to, obviously in 2021, 2022, we start seeing all the mails that these guys are sending on Iceberg list, but we just didn't know enough about what they're talking about to really think we can do it justice. So, guys coming from, like Ja said, all these communities, GeoParquet, Havasu, GeoLake, it's really confusing for us, like what these projects are, what they're doing. They're talking about really deep stuff like WKB, WKT encoding, like partitioning from like Microsoft, Google, Ubers, and like Geo kind of predicates. It's all very hard to understand for an Iceberg developer. But I think what really convinced me, I think Ja one day flew down from Seattle and we had a coffee, and I asked him like, oh, you're really passionate about Geo. Why do you want to contribute Geo to Iceberg? And he told me our customers don't want to get locked in. They want their data to be kind of open format, so any engine can support it. And I think, really, wow, that's really like kind of the goal of Iceberg, to be a common format for all kind of type of data for any engine. So I think we have more common points in common than difference, and maybe we should tackle all these technical challenges to make this happen. So that's how we started to work together. And so we think of the first principle, like, okay, forget all this hard stuff like partitioning. What's the minimum we can do to get started? And we think, oh, well, let's just add a type in Geo, a Geo type to Iceberg. It turns out this project itself took the year, but I think we learned a lot from this, and we can continue after this. But this is the building block, I think, for everything to come. So first, why it's important to define a type in Iceberg, geotype. So obviously, you can store geodata today even without geotype, right? You serialize it into a byte, a string, struct, whatever. The problem is it's not standard, right? So only your engine is able to understand that. Another engine doesn't know it's geodata. Also, if Iceberg knows it's geodata, it can do optimizations. So Iceberg as a data source, one of the main optimization is the filter pushdown. The query engine like Spark or Trino push down the filter, and the data source like Iceberg filter out the data that doesn't belong in the query. And so if we understand the geo, we can actually do filter pushdown for geodata. Otherwise, we cannot. We don't know. It's a black box to us. So that's why to define a type. If you ever need to define a type in Iceberg, there are two requirements. One is Iceberg sits on top of data files, right, like Parquet, Avro, ORC. So we need a way to how to encode the geodata into those data files. And the second one is the metadata. So Iceberg, for the filter pushdown, maintains statistics. In Iceberg, we call them metrics, column metrics, for all the columns. And for geo, we need to define what does it mean, metric, like what does lower bound and upper bound mean for geo. So these are the two kind of fundamental questions we try to answer for Iceberg Geo. For the first one, how to encode the geodata, we need to see, what is geodata? Unfortunately, for us, like this is already kind of a very understood problem, right? A lot of databases have supported geo for a long time. So they have a body in the geospatial domain called OGC, is a standards body. It stands for Open Geospatial Consortium. And they have already defined like a class hierarchy of geodata. So all this is geodata. If you ever use, even if you don't know much about geo, it's not very hard to pick up. If you ever use a map in your life, you will understand this quickly. Like for example, Google Maps, if you click on the Google map, you get a point, which is a set of coordinates, X, Y, Z, potentially, if it's three-dimensional. A set of points make a line or an edge. A set of line or edge make a polygon, and then you can have collections of any of these things. These are all geodata that you should be able to store in the Iceberg geotype. For the encoding, we're also very fortunate that OGC body also specified how to encode all these classes. And they really like the acronym, so they make one called WKB. It sounds really fancy, but actually it just stands for well-known binary. I think it's well-known in the geo domain. So the it's pretty much a very simple kind of encoding specification where it's just a set of bits that represent a geodata. The first bit is byte order, then you have some bits representing what class in the geo hierarchy, and then a class-specific encoding. So I think we talk a little bit, but we think, why reinvent the wheel? And to be an open format, you want more compatibility, so we just use what most of the ecosystem use and decide to use WKB to encode the geodata into the data file. So that's pretty easy so far. A little bit harder is the metrics. As I mentioned, Iceberg needs to keep statistics about the geodatas. And one of the most important ones is the upper and lower bounds. This is what it used to prune out the files that don't match the query, right? So we have to think, what does this mean for geo? Fortunately, geo also has this concept. It's called the bounding box. So if you think about it, like you have a lot of geodata, and in the geo world, to make a bound, you draw a box that kind of covers all the geodata that you want to bound, like all the geodata in your file, your row group, whatever. Like on the right side, I have like an illustration of bounding box for all 50 US states, right? And the property of a box, or even a cube, this works for 3D as well, is it can be defined by 2 points. There's like a lower point, which is x min, y min, is z min for 3D, and then a max point, x max, y max, z max. And so both of the points are themselves geodata, which is great, because in Iceberg, as of now, the bounds actually needs to be the instance of that column. So this works perfectly so far for Iceberg. There was only a little bit of discussion in Iceberg community about how to encode the bounds. Initially, we were thinking, oh, why reinvent the wheel? We use the WKB again. But I think Ryan Blue, he made a nice observation that in Iceberg, the metadata size is very, very important because that's on the critical path of reading and writing the Iceberg table. So he said, well, we always know it's a point, so we can make some optimization. We don't need the first bit. We can always hard code the bit order. We can always assume it's a point, so we can just get an even more compact representation of the bound by just concatenating the coordinate values of the point. So we have a nice compact bound representation. Cool, so that's the data file, metadata file. So sounds like we're done, right? You think so. But actually, we're only getting started. It turns out this was only the first step. We figured out later on that if we don't have to type in Parquet, all this falls apart. And I'll have to explain why. So Parquet is another specification, and Iceberg is built on top of Parquet. And the same problem happens if you don't have the geotype in Parquet. Like Iceberg can write the geodata as WKB binary to Parquet, but another person reading that Parquet file won't know what that is. It's not standard. So that's why you need a geotype in Parquet. What's worse is, Parquet also need to do filter pushdown. So there's, filter pruning at the Iceberg level to prune out files. But what if you have a very big file? You want the file format like Parquet to prune out row groups as well. So Parquet need to understand the geotype to do pruning at the lower level. And actually, one interesting thing is the implementation of Iceberg writers. Iceberg writers actually end up writing the whole Parquet file and then just taking the Parquet stats, copying to the Iceberg metadata. Obviously, this is much simpler than rereading the Parquet file after writing, right? So then we run into a chicken-egg problem. If you don't have the stats in the Parquet, actually, we will never have stats in Iceberg. So we have to actually go to Parquet community to add the geotype there. First, we were trying to see how to do that because there's a different community. But we're very fortunate. When we make the Iceberg proposal, it's open on the dev list. And there's one Parquet PMC member called Gang Wu who was very nice and was really active and said, he'd see what we need in Iceberg, and he said, I will drive the effort in the Parquet side. So we work really closely, so me, Jia, and Gang, just to make sure the specs are defined the same way in Parquet and in Iceberg for encoding the geodata and also the bounds for the geodata. So we're happy to see this kind of cooperation among the community. And what was even more cool was Chris Holmes, he was the founder of the GeoParquet, which was the extension. He was also on board too and agreed to kind of make the new, put the GeoParquet stuff into native Parquet. So everything now is all in sync. So this is actually quite huge if you know the history of the division of the communities. So are we done yet? No, so actually, again, we just got started. And to our kind of surprise, it took many more months of discussion. And this is where we kind of have to get into the weeds. I didn't initially want to get into the weeds of the geo domain. It's quite complex. but it looks like you cannot escape that. So the problem of Geo is like, it's not like another type in Iceberg, like integer type. No one ever debates like the two engines reading the same integer value. There's no debate what is 0, what is 1. But in Geo world, it's not the same. The same Geo data can be interpreted to mean different things on the Earth. What you have to do is actually, Iceberg as a spec, we have to be very clear. When the writer writes geodata, he has to annotate it with enough information so the reader knows exactly what the writer meant. Otherwise, you have very subtle errors or even disastrous errors, right, when you interpret this data. And there's two main class of problems here. One is, remember the OGC class hierarchy, the point. What does a point mean on the Earth? Like, how do you map a point bytes into somewhere on Earth? And also edge. Edge is 2 points. How do you interpolate the edge between the 2 points? So this is a tough questions. Fortunately, again, the geo domain, they have some advancements here. So you probably have seen this in school, like coordinate reference system. This is the answer to the first question. How do you map a point to somewhere on Earth? And the coordinate reference system is a system where you define, it's pretty complex, but I think you define a coordinate plane in the 2D, you estimate the shape of the Earth is a sphere or an ellipse in 3D, and then you project that 3D onto the 2D. So it's a whole, but it's a well-studied domain. And the OGC, fortunately, the standards body also have a standard for that. They actually made a database of all known coordinate reference systems out there, and they give you an SRID, which is like a primary key into one of those coordinate reference systems. So for most databases, you provide an SRID when you write the geodata to tell it like what I use to generate the geodata. So we think it's okay, but the problem is like the OGC, I think it didn't catch up with the modern times, because modern times you actually have CRS that are beyond what the OGC know about, right? You want a custom CRS, and I think there were no good standards for that. There's a lot of kind of almost religious debate there, like between ProJSON and some other ones. And yeah, we were like kind of getting a little, we didn't really know what to do because people kept debating on this one. Fortunately, we take a step back. We think Iceberg, we're just like a format. So we don't want to dictate to people what they should and should not use. We just want to support what most people are using. So we allow like SRID and ProJSON, even if it's like maybe not formally stamped by the OGC. And we can support other ones as well. So we now add a CRS as a type parameter for geotype. And you can specify the default or an SRID value or a ProJSON value. And Iceberg implementation, if it's a CRS that we know, only then we will do the filter. Otherwise, we will say even we don't understand the data and we will not do the filter pushdown optimizations. But that's okay because these are optional things, right? Different implementation can choose to do filter pushdown for CRS that they know, right? So that's the first part. The second hard question to answer was edge interpolation. So edge interpolation is, again, edge is modeled in the geotype by 2 points. And there's actually, I don't know if you can see, this is like Dimitro from Snowflake. He provided this nice diagram to illustrate. Like an edge, Cartesian edge, the normal edge between San Francisco and Berlin is a straight line. But if you ever take a flight to Europe, like you don't go in a straight line. You kind of like, because the world is sphere, you kind of go across Arctic Circle and go back down. So actually, we want to model this realistic kind of like edge. So in the database world, PostGIS, I think, was the first to do this one, or I don't know the first, but the early runner. They make 2 types, geometry type and geography type. Geometry is for the straight line edges, and then geography is the edge where it considers the curve of the Earth. So we think, okay, maybe that solves the issue. But again, we got bogged down in a lot of really mathematical debate there. A lot of people coming in and even criticizing the geography type of PostGIS not being specific enough. They say it's not geodesics and like debate the name for a long time. It got really kind of ugly. And then I think later on, again, like we take a step back. Like Iceberg, we don't want to get into these debates. We want people to just be able to use us and be able to store what most users want. And so we say, okay, we can make the edge interpolation algorithm parameterizable, and we support these kind of values. These are the most common values. I think Menelaus from Databricks provided us. And so, same thing, Iceberg implementation, we can store these values, but then like only if we understand, like if it's the default, for example, then we can do the filter pushdown. So maybe that part I could double click into. So the bounding box, right? Like the bounding box for the edge between San Francisco and Berlin, if it's a Cartesian bounding box, a Cartesian edge, then it's easy, right? You just take the latitude of Berlin, latitude of San Francisco, and the longitude as well, and that's the box. But if it's a spherical edge, the box has to go way up. It has to, because the edge goes way to the north. So the bounding box needs to actually take that into account. So you don't want to do the filter pushdown for edge interpolation algorithm that you don't understand. So all this is to say, like, okay, there's a lot of technical discussion there, but after 1 year of discussion, we got the two types into Iceberg, the geometry and geography type. Geometry type is for most use cases, I think, is fine because it's faster. The linear edge interpolation is always faster for a computer to calculate than like a spherical one. And it's usually fine if you're doing like local kind of like data in a city or a county because you don't have these edges that you need to really model based on the sphere of the Earth. But on the other hand, if you do, then you can use the geography type. There you can use any kind of like, or the supported edge interpolation algorithms. You're limited though, the CRS has to be a world-spanning CRS. And there's also one thing I don't think we have time to cover is like the bounding box has to be wraparound. Like there's some case where if at the 180 longitude, it kind of like goes back to negative 180 and there's some objects in that line. So geography has to handle that case, but that's another thing. And then, so you would use this if you're trying to map things like shipping lanes or airplane routes or something that kind of goes very far. So pretty much that's the summary. V3, we're really happy, like me and Ja, to get this through. The Parquet committee and Iceberg committee worked hand in hand, and then like in February 2025, like a few months back, we passed a vote to adopt that formally in both the Iceberg and Parquet specs. And Iceberg V3, which is like this one and many other types, all was formally adopted only a few weeks back in May. And so this is now officially part of Iceberg V3. It was really cool. I think this is the biggest project we've done in Iceberg, or I've done. And just like people from so many communities, GeoLake, Havasu, GeoParquet, Iceberg Parquet, and then so many companies like Wearable, Snowflake, Databricks, Apple, ESRI, Carto, like engineers who usually compete with each other like in the same room, trying to see how to advance the whole ecosystem. I think it was really, really cool. And yeah, I think Iceberg as a community really has this principle of doing the hard thing. Like we take the time, like beyond I think what one company can invest in, but just like we keep going until we support the majority of use case. Because I think Iceberg, what's the point of this open table spec if the people don't want to use the spec, right? So even though a lot of time we want to, we think we cannot progress, eventually we get to a consensus. And I think the patience has paid off. We have some ripple effects after Iceberg kind of adopt this spec because now it's kind of the first door, I think, into the wider big data ecosystem. Like Delta Lake has a RFC like a few days back about adding geotype to that. And then Spark had the SPIP to add a geotype to that, working with the Sedona community. And so I think a lot more open source projects will start to adopt it after Iceberg has adopted this one. So I'm super excited for that. And now Zhao will talk about what you can do with this.
Sure.
Yeah.
Great. Great, so much meat, right? Now let's talk about some cool demos, right? So the demo I'm going to show you is actually a combination of these ongoing PRs. So it is using the Iceberg and Apache Sedona and Apache Spark all together. So after all these PRs are merged, so you can actually use them in production. So now let's see some example here. Cool, so this is a table. Let's create an Iceberg table here, right? So this table has two columns, so ID column and the geometry column. So the geometry column is having the geometry data tab. And when you create this table, so in the table properties, you're going to specify the format version to be a V3 because this is a V3 feature. Now let's put some data there. So the first data we're going to put there is two line string object. So line string A and B. So we're going to append those two records into the Iceberg table. And now let's put some more data there. So line string C and D. So then we append those to the table. And then another append operation, so line string E and F, so another operation. So now if you look at this table overall, so you have 6 records, so A, B, C, D, E, F, and 6 line strings. So if you put those on a map, so you'll see all those line strings. Now, let's do some deletion operation. So I want to remove the line strings that intersect with this orange polygon. So how do we do that? So the way we do that is we introduce a spatial predicate called ST crosses. So this is a spatial predicate coming from Apache Sedona, but you also have the same predicate across the board, like in PostGIS as well. So what ST crosses does is it takes two input. So the first input is the geometry column, the one that we already have in the Iceberg table. The second one is actually the polygon, the orange polygon shape. It is encoded in this WKT text string. So you put that into as a second input, and then we actually run the delayed from statement. So eventually what you have is the following, right? You have a table that has actually the two-line string B and C got removed from the table. Now, if you look back, we have done actually 4 operations, 4 transactions on the table, and the Iceberg table now has 4 versions, right? So actually, if you look back through the Iceberg snapshots, you'll be able to see all the 4 snapshots and also the corresponding operations associated with each other snapshot. So that is the power of Iceberg. Now, you can also do time travel across different versions, right? So you can actually jump right back to the snapshot that is right before the deletion. So that has actually 6 records. You can also jump to the snapshot that is after the initial append. So that has only 2 records, right? So which is great. Now we have a little bit more advanced example here. So we have 2 tables here. So there is a target table. So it has a few records, right? So we have another source table. So this source table has 3 records. However, here is a catch, right? So if you look at the 3 new records here, so we want to put the 3 new records into the target table. We want to sort of like merge them together. However, if you look at the line string D, so it is actually a duplicate of the same record in the target table. And the second line string E, it is actually a same record. There is a record E in the target table, but the geometry shape is different. The third record, line string Z, so it is a new record, right? Now we want to merge these 2 tables together and, of course, update the necessary records. So that's how you do it. So you can use this merge into statement in Iceberg. And so it is probably a little bit hard to see the details here, but essentially you have this, it is even harder for me to see. Oh, nice. Yeah, cool, yeah. So you can see this is a condition here, right? So first, when the ID matched, so you're gonna do a check. So if the 2 geometry are the same, if they're the same, you don't actually merge the new geometry into the old table. But if they don't match, you can insert that record into that table. Now, after this query, that's what you get. So you get you get actually a table that has 1, 2, 3, 4, 5 records, right? But pay attention to the record D here. So record D, that was a duplicate, so we don't actually insert a new duplicate, right? And the record line string E, so its shape got updated. And line string Z actually got inserted into this new table. So basically, this is observed with merge. Cool. Another cool thing is the spatial schema enforcement, right, with this native geo data type. So suppose you already have a table, like what we already showed you before. Now I have a new table. I want to append this new table into the existing Iceberg Geo table. And this table, in the schema, it has 1 more column. So this 1 more column is the number column. So now if you want to append this table to the other table, to the existing table, it is going to arrow out, tells you that the schema does not match. And you can actually also do schema evolution on the Iceberg Geo data table, and you can actually alter the schema to make it have this new column, number column, and then you can actually append this new table to the existing Iceberg table, and then it will work. You can see that we have a new table that has both new table and the old table together. And in the old table, because we initially did not have the number column, so the number column has the value now. But basically, they work together and pretty nice. Cool. another cool thing about the Iceberg Geo data type, also Zihong mentioned, is you can actually leverage the bounding box to perform really nice filter pushdown. So this is a really simple example here. So suppose we have Iceberg table with multiple points. And so you see there are multiple points here. And the color of each point actually, like points that have same color, meaning that they're in the same parquet file. They all coming from the same Iceberg table, but points that have same color, they are in the same parquet file, parquet data file. Now, suppose we have a spatial query or spatial filter. So that is this polygon shape in there. So it is the filter area, right? Now I want to find all the points that fall inside this polygon. So what do we do? So in Iceberg, and as we mentioned, because Parquet and Iceberg both have the native geo data type, you can actually have bounding box statistics on top of each Iceberg file. So basically, you can have a bounding box inside each Parquet file that actually help you to perform data pruning. Now, if you run this query, right? So you can actually use a spatial predicate to perform this. So this spatial predicate here is called st-intersect. So this is a spatial predicate coming from Apache Sedona, but you can also find the same thing in PostGIS and somewhere else. And you can run that, put that in the Where clause, and run that directly on top of the Iceberg table, right? So it will find the points that intersect or fall inside this polygon, this filter area, right? So the output is 3 records, right? So only 3 points that fall inside this filter area. So you can actually verify that if the filter pushdown actually kicks in or not. So if you actually use Sedona, you can actually print out the curve plan. So if you look at the curve plan here, right, you can see that the filter st-intersect got pushed down to the bottom, to the bottom of the curve plan, meaning that it got executed really fast at the beginning. So it did perform the pruning. Cool. So another cool thing you can do with Sedona on top of Iceberg is the geospatial clustering or indexing, right? So as you probably already know that, so because you already have this kind of bounding box statistic in Parquet and Iceberg, right? So this actually have a huge impact on the curve performance and filter pushdown. So if you want to have really good performance for really good data pruning performance for Iceberg tables for spatial data, so you actually need to order data based on their spatial proximity. So there are so many ways to order them, but essentially the idea here is you sort of want to make sure that you preserve the spatial proximity within each Parquet file and Iceberg table, and such that the bounding box is really, really tight, right? You can, when you have a spatial filter, you can prune as many bounding boxes as possible. So in Sedona, we have this function called Hilbert curve, right? You can actually order the spatial records you have in Iceberg table by the Hilbert curve ID or your geometry. So you have, say you have a polygon, you have a line string, you have a point, you can have actually you can take the centroid of your geometry and get a Hilbert curve ID of that geometry shape, and then you can order the entire table based on the Hilbert curve ID. So this doesn't have to be like, because this, you see this is taking the centroid of the geometry, right? Because this doesn't have to be 100% accurate. As long as you can preserve spatial proximity, it is good enough. It's going to have really good, really tight bounding box already. Cool. I think, yeah, that's all for our presentation. And do you want to talk about survey right now?
Yeah, again, just quickly.
Yeah.
There's a completed survey for us. Thank you.
Yeah, so there is a, I think on your app, so there is a survey for each session. So if you like our talk, give us, fill in the survey.
Yeah.
Okay.
Yeah. Thank you.